Just gonna get us banned. Oh, like some kind of weird dystopian fisherman. Oh, okay. Hey everyone, so we have a fun teardown of the Liquid Freezer 3 today. We have a full review of this on the channel. It just went live, I think yesterday at the time this video goes up. This is gonna be a more in-depth investigation into why some of the behaviors were the way they were when we did things like the pressure testing, like the 3D scan, where we saw basically the only true weak spot of the cooler. Overall, we said it's the best cooler that we've tested for noise normalized thermals, period. And we did make a recommendation for it. However, this teardown is going to look into some of those shortcomings, but also try to evaluate what's changed. Because if you look closely at this pump block versus the original Liquid Freezer 2, which we have torn apart here from many years ago, the assembly is massively different. And so the first thing we're gonna look into is how they've changed the actual impeller and the housing of where the liquid flows. Because that potentially contributes a lot to the thermal characteristics, depending on if they've widened those channels to allow more water to pass through more efficiently. Maybe they've changed the microfin density. That's what we're gonna be looking at today. And additionally, I really wanna get in there to see if there's any type of deflection where when you torque those screws down, is it applying a pressure that causes that sort of central bump we saw in the laser scan? So we're gonna take this apart and have some fun learning about how it's built. Before that, this video is brought to you by Thermal Grizzly and the CryoSheet graphene pads. These CryoSheets are molecularly stacked in the Z-axis to encourage vertical direct thermal transfer from the IHS to the cooler. CryoSheet pads are made to be easily applicable for a thermal interface and completely avoid paste dryout because it's not paste. It makes them particularly useful for long service life systems with minimal maintenance. They come in multiple sizes for suitability on the most common laptops and desktop CPUs, and you can learn more at the Thermal Grizzly CryoSheets at the link in the description below. First thing I want to do is a couple loose ends we had, where in the review we were already at 30 minutes, so it was like, you know, let's leave a couple of these things for the teardown, and one of them is going to be the sizing of this cold plate. About 40 millimeters by about, let's call it 44. And let's look at one of the original. This is the actual OG that we reviewed, I think. You can tell it's even patinaed a little bit. This one hasn't been used in years, so 44, that's the same, and 40. So it's the same size cold plate. It doesn't mean anything about the microfins though, so we'll still need to look at that. So for the blocks, these are obviously very different. Not gonna spend a ton of time explaining to you how they're different. You can look at it. The biggest change though is the pump cap, which we've already detailed heavily in that review. And this is kind of interesting because, first of all, from a repairability standpoint, the option of just pulling off the entire VRM fan, which is the most likely part to fail. Tiny fans are always the most susceptible, vulnerable to long-term failure from things like dust, stuff like that. They just don't have the power to really push past it. They'll burn out. But being able to replace the entire unit is a lot more user-friendly without a huge amount of extra waste, certainly less than shipping the product back and forth. Makes it a lot more repairable, maintainable, which is a good thing. In theory, if they wanted to later maybe sell detachable alternates or something, or I don't know if they're planning that, but it was the first thing my mind, being in the gaming world, jumped to was, how can this become DLC? The impeller, I'm thinking, is going to be in here. It's the only thing really large enough to hold it. And it's kind of interesting, the liquid flow is gonna get pushed down here over the microfins. I'm gonna start with the actual cooling part, because I really wanna look at that impeller and the microfins. And we've got an old plate here, disassembled from one of our repair kits previously. And we'll use this for comparison against the new. And this one's got, I was gonna say a little bit. We're gonna go with a lot of bit of gunk on it. Okay, so today we're gonna be working on our soldering mat. You can grab this on store.gamersnexus.net if you want a highly rugged and high heat resistant surface for soldering projects, model building, doing mechanic or other work that you want a rugged surface to work on, plus a bunch of tool holders and component holders. So start with a quick kind of overview of the anatomy of a liquid cooler and the components, just to get everyone up to speed. This is the cold plate. The cold plate has microfins on the other side. This, this is the leaf spring specifically. This is not standard. You get inlets and outlets in there that are made within the plastic shell. The plastics for liquid coolers can typically handle about 60 degrees Celsius for specifically the liquid temperature. That sounds low when you consider that this is contacting something that might be closer to 90 degrees Celsius or 70, 80, whatever it may be. But the liquid temperature runs way lower than the surface temperatures of these things. So 60 is pretty standard. I don't know what Arctic's specific rating is for their plastics. I do know that Asetek, though, starts to fail at 60 degrees Celsius. My understanding is that's pretty common as a temperature, or plus or minus 5 degrees. There's almost always a PCB with these that's down on the pump block. The complexity of the PCB depends on presence of things like RGB LEDs and LCDs, other functionality they might have. PCBs typically have soldered-in wires that are not separable from the board without desoldering them or cutting them. And then after that, we run into, of course, the tubes. Now these tubes, there's typically two common types. There's a more rubberized one, which is what this is. The benefit of the rubberized tube is that it's more flexible than the alternate that we'll talk about. The downside is there's a little bit more permeation over time where the liquid will permeate those tubes, so you have some natural liquid loss. Typically, it's about 5-6 years for anything serious to be lost and maybe need a top-up. The other type of tubing is a hard corrugated Teflon lined tubing. That's what Cooler Master uses. We'll show some old examples from their Sidon series. That one's more resistant to permeation and loss of liquid, but it's much more rigid, and if it cracks, then you have worse problems. Inside of the actual barbs, this area of where the tubes connect to the rest of the body, normally there's like a piano wire that kind of holds it and secures everything. Those come up to the radiator. We have an old 3D animation that shows how these work, but this has a split channel in it. The liquid goes in one side, comes out the other side, so you can think of it as a hot and a cold side. And then the radiator itself, this one's a thicker radiator. I think this is a 38 millimeter. So this is the outer shell of the rad. Let's just measure it there. That's 35. If you measure it at the bump, it's 38. But the actual inner part of the radiator is a little thinner than that still. This is thicker, though, and that's a large part of the performance that Arctic has. But let's start with just draining it. I'm going to try and do this non-destructively. We'll see. Sometimes it's kind of hard. Okay, there's our cold plate. That is nice and new. You can see the difference in the Gen 1. This is the one we replaced after they contacted us about some of the units being in a bad batch. So the gasket immediately, this looks pretty different. This would have been the original gasket, and we'll compare these once they're both out, but that already is a different style to it. Let's pull that out. Which, not surprising, because I think the gasket choice definitely has a lot to do with the debris buildup in a loop. So that was mounted like that, I think. And then we're going to drain this water out. I don't have a bucket nearby, so this one actually might be kind of challenging to drain just because it's got that angle in it. Just going to get us banned. So the liquid for basically any AIO liquid is going to, oh, okay, there was still some more in there. Typically liquid is a propylene glycol. The higher percentage of distilled water, the better. The propylene glycol is used for a couple scenarios, but one of them is kind of a natural resistance to corrosion, debris buildup. Another one is actually shipping, so it gives a better range for the freezing point, and you put it up in colder environments, then that'll kind of increase the range that the cooler is viable or can be stored and shipped in. I'm seeing two clear channels in here. We'll try and pick this up on the camera, but there's one channel down in there, so that, actually you can see it right here, this piece. That's a channel, and then right next to it is another one. So these are going out ultimately to the tubes through the impeller area. You can see that flow guidance here. So let's compare this to the original. I have one taken apart here. Unfortunately, I don't think I have the impeller with this one, but we have some old B-roll of it. So you see the channels, the design here is massively different. Where previously you had this kind of slope in, and over here as well, hit the impeller, and the cold plate was actually mounted up here, higher up, kind of closer to the camera. So very different internal chamber. Let's take a closer look at the important part down here. the actual microfins, and sort of despite the aged appearance of our old one here, see if they have any similarities. Its fin area is about 21.6, 28.84. Now there's a vertical component to that too, so we actually can't do the area calculation obviously from something that simple, but so I mean that's the same functionally. It's also the same. Okay. I don't know that the density has changed. We'd have to put it under a microscope and count. The vertical would be interesting to know though. All right. It's like 3.5 or so. Oh, this one. Yeah, it's definitely shorter. I just make sure maybe they changed the milling around the channel. Yeah, okay. That's kind of a crazy height difference. It's about 1 millimeter, and that's going to contribute in a big way because more surface area. So for each of those fins, you're now 1 millimeter taller. I'll go put these under a microscope to check the fin density as well, but the height alone is going to contribute a lot to the cooling capabilities of this. More potential to get heat into the cold plate efficiently and get it out through the liquid into the radiator, of course. So big change there. Additionally, if you look closely at these, they have changed the sort of channeling. So they're chewing into more of that surrounding copper. It's the same overall size as we saw earlier. But if you look on either side of this microfin stack, they've got some channeling around it. Whereas on the old one, it was only from current orientation towards the camera and towards me where we had the channels there. So that is another change. Now, how specifically that manifests in performance, I can't tell you. You really would only be able to tell that from simulations because we can only kind of look at it holistically for performance. But another big change nonetheless. I think that height is the largest difference we're seeing, though. You can see the differences here as well in the design where they've changed the actual shape of where the water is going to hit and get diverted into it. And then now on this one, there's this kind of curvature up on the lip over here. So anyway, that's the design of the cold plate. I'm just going to start removing screws until we find what we want. So that, you might be able to do a fill there with like a syringe or something, but I would just take the cold plate off and fill with the bottle from the bottom. That's what we normally do. Okay, let's remove more screws. We're going to remove the PCB here. That's going to give me the best access. Wow, that's in there. All right, that is all 3 screws for the PCB. I'm going to see if that is loose yet. Some coarse threaded screws hidden down the side. Actually, I think that's the same screw as what the PCB he was using. We got 2 more back here. Vitaly's about to witness a stabbing over here. There's another screw down there. Oh, we can get it, that's good. Okay, all right. All right, okay. So that screw just goes to a plastic back cover. There is nothing to discuss here of interest. This is so many screws. This is a liquid cooler that has probably some of the highest count of screws I've worked on. I won't be able to really comment on if that's good or bad until we get in there. And the most important thing is it doesn't leak, so. Okay, we're getting somewhere. Cool. It might be possible to non-destructively disassemble this. There's the impeller. That is a large impeller. Now they had a large one with the old model too. With the magnets and wet. Oh, like some kind of weird dystopian fisherman. Okay, we've made it to the interesting part. Massive impeller. This is the direction that these AIOs, the CLCs have been going. So EK also did this. The original liquid freezer used a relatively, for the time, large impeller too, and a metal one, which this also is. All a big improvement over what used to dominate the market, and that was Asetek's tiny yellow plastic 3-pronged impellers that